All right, let's look at this problem. It's kind of talking a little bit about household wiring and such. Let's see if I can find a marker here. I mean, a colored pencil here. And so we're going to just look at, these are just somewhat made up numbers, but we'll get an idea. So in your household wiring, you have an outlet, and it has the two places where you plug in prongs. It's kind of exaggerated how the difference in size is, but there's a bigger slot and a smaller slot. The smaller slot is what we call the hot. The hot, and then the other one is called the neutral, and then this one is the ground. You know, you saw in the video, the ground is for safety. When we're wiring things, the neutrals, if you look in your breaker box or if you see in your walls, the neutrals are the whites. It's not really working out to be whites. And then the hots are the black. This isn't black, it's actually blue. But anyway, the hots are the black that go to the positive side. And they're all connected in parallel. So you see this hot is connected to this hot that all goes to the positive of the source, whereas the neutrals are all going to the negatives of the source. And then only at the breaker box, the grounds, which are usually the bare copper, are also connected to earth ground at your breaker box, usually, where it comes in from the power system. Okay, so the ones that are dangerous, the most dangerous one is the hot. I guess maybe that's why it's the small slots, because you don't want anything to get in there and touch it, because that's the biggest live voltage. This is AC, which is sinusoidal, but we'll just go ahead and use RMS values. So we'll say this is 120 volts for now. Okay, but that's AC. It's not a flat 120, but it's an effective 120. All right, so we have this person here, and he's going to be a dumb person. He's going to stick his hand into the outlet kind of thing, or stick maybe we'll say like a screwdriver into there. So let's say he's got a screwdriver that's metal, and he's going to stick it into the hot, which is like it says, don't do this at home, right? We all know this by now. Okay, so we're just going to make up some numbers here for the resistance of a person. Let's say his arms each have 200 ohms resistance, internal resistance. His body core has 100. Legs each have 200. Maybe 200. Maybe across the head is 100. The skin, I think I looked up just some numbers to get some idea, is maybe about 1,000 ohms, the resistance of your skin. Once your skin gets burned away, whatever, then you have more connection, so that's bad, but initially you'll have some protection from your skin. And let's see, we're going to pretend like he has some sort of rubber boots on, some sort of insulating boots, and let's just say R of the boots is, I don't remember what I had for that. Let me see if I put a number in my notes. Pretty high. We'll say that they're insulating things, so I had 1 times 10 to the 9th ohms for that. So good insulating boots protect you from electrically insulating boots, right? Protect you from current flows. And let's say that the system, like from the floor to the ground of the earth, has a resistance of 10K. Again, it's just fairly made up numbers. Okay, so we're going to see what happens to this guy when he sticks something metal into the hot slot of outlet. All right, and so remember, electricity is going to flow if we have a closed loop, and so we have to figure out the closed loop. The closed loop is going to be, say, starting at the source to the hot, going through one arm, through his body, through both legs, to the ground, and then back through the ground, back to the negative terminal of the source, and it's closed in. All right, so the first part A says draw the circuit if his hand is connected to the hot or touching the hot. And so we would have, let's just start with this is his hand or his arm. And then we're going to have some resistance for the skin. All right, and then it's going to go through the hot wires to the source. All right. Usually AC sources we draw with like a little sine wave inside. To remember it's AC, but we'll just, for our purposes, we'll just treat it as 120 volts. All right. For resistors, all the equations work pretty well. All right, so the skin is there, the arm is there. So this is 200 ohms. This is 1,000 ohms, we said. And then the path comes through the body. So we'll do something like this. So this is 100 ohms for the body. And then we've got the two legs, right, 200 ohms each. Ohms each for the body. And then we've got the boots. I'm sorry, for the legs, 200 ohms each for the legs. And the boots are 10 to the 9th ohms each. So the boots are going to be a big block to the current flow. And then we're going to come back through the earth and the building and what have you. We said that was 10,000 ohms. 10 times 10 to the third ohms, 10k ohms. All right, so this is what our circuit would kind of look like, whereas this is the person, and then we've got the boots and the building and so forth. Okay, and so when the person makes contact, then there still is the neutral. Well, the neutral is not connected, so there are these other paths, but they're not part of the circuit right now because the person has closed the circuit. Normally when you plug something in, whatever it is you plug in will contact the hot and the neutral and close the circuit and get electricity like it's supposed to get. All right. Okay, so this is a thing, the way it's not supposed to happen. So we got our circuit. Okay, find R total. So we want to find the total resistance of this path so we can get the current, I sub S maybe we'll call it, coming from the source and flowing through the person. See how bad it is. Okay. So R total, so if we're looking at this, we'll see the skin is in series with the arm, which is in series with the body, right? But then we have the two legs and the boot, each leg with its boot in parallel with each other, and then that closes together and touches the ground and goes this way. So R total would be 1,000 for the skin, plus 200, they're in series, resistors in series add, so plus 200 for the arm, plus 100 for the body. I'm running out of room. So plus, we have 200 plus 10 to the 9th in parallel with 200 plus 10 to the 9th. All right, that's there. And then another thing in series is the 10K plus 10 times 10 to the third. And that's all the resistance across the source, right? So we're looking here, that's all the resistance in the path. So let's see what our total is. Let's just add up all these extra ones here. So we've got 10,000 plus another 1,000 is 11,000, and then 300. All right, we got 11,300 from those plus this combination, right? Which is 1 over 200 plus 10 to the 9th plus 1 over 200 plus 10 to the 9th. So it's not times 10 to the 9th, so it's really basically 10 to the 9th because 200 is so small compared to that. But let's go ahead and put it in the calculator anyway. So 11,300 plus 1 divided by, in parentheses, 1 divided by 200. Whoops, I need parentheses there too. So it divides by all this, 200 plus 1E9. And then add to that another one. And so if we remember, when we have two things that are identical, that are in parallel, really what comes out is just half of that. It just cuts it in half. But let's just go ahead and plug it in for practice. 200 plus 1E9. I think it'll close the parentheses for me. All right, so did we do it right? So we got the 1,300, then we got the 1 over the 200 plus big number. All right, so we end up with still a big number because half of 10 to the 9th is still large. So our total is 500 times 10 to the 6th. Basically, it's the insulation of the boots, right? Ohms. And so I equal IS is going to be VS over R total, right? So the IS, if we draw a little circuit, VS, IS, R total. All right, so this equation comes from this. So IS is just VS over R total, 120 over 500 times 10 to the 6th. Going to be a small number, right? 120 divided by 500 E6. 240 nanoamps. Right, 10 to the negative 9. And so 200 milliamps, so AC is much more dangerous than DC, right? That's the frequency of it going up and down. It messes with your heart muscle rhythms. You can clamp your heart and so forth. But 200 nanoamps, or 240 nanoamps is fairly safe, right? I think it is. Oh, where is our book? I don't have our book. Let me see if I can. Let's just find a table real quick online. Sorry for the delay. I should have done this ahead of time, but all right. So 1 milliamp is usually harmless, but may cause a tingling. 5 milliamps could be a painful shock. This is all according to AI, but it is 200 milliamps can be lethal. All right, and so 200 times 10 to the negative 3, whereas this is 240 times 10 to the negative 9. So this is much more in the safe range. This is lethal. Somewhere in that range. Again, it depends on your internal resistance and lots of different things. Which path. This is a fairly dangerous path because it goes by the heart, right? And so, but in this case, our rubber boots have saved us, right? Let's say now, redo if we were outside and we had like an extension cord or something and we did the same dumb thing and we stuck the something into the hot terminal and we were on wet ground with bare feet. All right, so what would happen then if we were now a person, the resistance, so he's touching the ground, he still put his hand in the outlet, right, and so we've got the source, something like this, and so the circuit would now be, we've got the 200 for the arm, we've got the 1000 for the skin, we've got 100 for the body, we've got 200 for each leg. I guess we can put the skin. We didn't really put the skin there. We probably could have. We'll put the skin in here. And so this was 100 for the body. This was 200. These are 1000 each. And then we've got, we'll still say it's 10K, 10 times 10 to the third ohms for the earth. And then we got our source here. Okay. And so now our total will be what? A lot smaller, right? It'll be 1000 for the skin, plus 200 for the arm, plus 100 for the body, plus 1200. Let's just lump these two to be 1200, right? In parallel with 1200, plus 10 times 10 to the third for the earth. Okay? And so our total 2, we'll call that. And so our total 2 is this 1300. Where did oh, and if we do this 10,000, we'll make it 11,300, same like we had before, adding those pieces up. And then 1200 in parallel with 1200. Remember we said two things in parallel with each other comes out, if they're exactly the same, it just comes out to be half. So half of 1200 is only 600 now, right? Because the boots aren't there. So if we have, so that becomes 11,900 ohms only for our total. All right, and then IS now is still VS over R total, because the equivalent circuit looks like this again. So we got the 120 now over 11.9. So 120 divided by 11,900. is 10.1 milliamps. So again, definitely painful. The thing that I looked up said, may cause a painful shock. And so the 10 milliamps, even though it can cause your muscles to contract on your hand, if you did it like you're grabbing something, you couldn't let go, right? So that's another thing. Our muscles are made to work with electricity, and so if we get a certain amount of current in, it may not immediately kill you, but then you can't let go, and then your skin burns away and anyway, this is kind of gross, but anyway, you get less resistance, and so then the current will go up and it gets even worse. And so that's why it's important to get people off if they can't let go, to get them off as soon as you can. We have circuit breakers and things also to help protect so that it doesn't get worse and worse. But so this would be a painful shock. Maybe you wouldn't be able to let go. All right, so all of this was just doing it from one hand to the foot. Much worse would be if you were super dumb and you connected one hand to the hot and one hand to the neutral. Right? So if you did something like this, what would happen? Right? If we did one hand to the hot, and one hand to the neutral, right? So that is connecting yourself basically in parallel with the source, right? And your heart is right here in between. You can't draw a heart for some reason. Right? So this would be, one hand to the hot, one hand to the neutral. I guess we can put some skin in here. But you're putting yourself right across the 120 volts. Your body is in parallel with the source. So even if you have boots on, the current is going to come from the hot and go back to the neutral through the power system. It's going to ignore your boots and all this. It doesn't care because it's got a nice small path to go around and go through here. All right, so if we had something like this, your R total would be 1,000 for the skin, plus 200 for one arm, plus 200 for the other arm, plus 1,000 for the rest of your skin, and then your back, right? So the total resistance is only, R total 3 is only 2,400, right? And so then the IS is 120 over 2,400, 120 divided by 2,400. So now it's 50 milliamps. So again, probably be very, very hard to let go if you were holding on to stuff. And so it might, the shock of it might force you back, but still, it would, in this case, basically your skin is saving you, right? And again, different skin is different. People's skins are different. If you have oily skin or if you're wet, this would be a lower number. Dry skin, it's a higher number. It's safer. Less current can flow through it. But in general, don't try any of this. Don't trust any of these resistances to keep you safe because there are lots of variables here. But anyway, hopefully that gives you an idea and a little more circuit practice.